Good morning all, and thank you for the opportunity to talk to you about this project. I usually start these sessions with a little confession. I am from Western Australia. However, I was born and grew up in New South Wales, so I share two loyalties. I'm also not a mining engineer. I'm not a mining manager. I'm a mechanical engineer. So apologies in advance if some of my terminology around the coal mining process are a little bit short of 100% correct. So the Australian coal industry is challenged by a number of things. Firstly, because we operate machines in a highly explosive environment, we need to control surface temperature, and that poses a lot of challenges both for the tailpipe and all surfaces of any product that's part of a mobile machine. There's a methane-rich environment, and that affects engines two ways. Firstly, any hot surfaces can ignite that methane, but certainly the engine may breathe that methane, and that may change the operating characteristics of the engine. We are challenged to reduce pollutants for the safe and healthy of the workers, and that's particulates, including ultrafine, so the very, very smallest of those components, as well as gaseous. The project that I'll be talking today is actually two projects. It spanned 3 years. I first spoke to you guys probably in 2014, in 2017, and today it's the wrap-up of this project. I want to review some key findings and share some of the results of the validation and trial work we have done. Today, the technology used predominantly to control emissions in underground coal diesel engines is a wet scrubber type system coupled with a wet filter, so a paper filter that you dispose of. In the future, and as Mark indicated in his discussion, Glencore and others are looking at electrification. Just like you've electrified plant, you will probably look to electrify mobile equipment in the future. But today and tomorrow there's the opportunity to achieve significant reductions in particulates without necessarily letting go of the diesel technology. This project work was funded by you guys through the association, through ACARP. For those that aren't familiar with the process, 5 cents out of every tonne of coal exported and produced does go back into research and development and other application engineering programs. I'd like to thank the industry monitors, some of those who are listed there and then others who aren't. Greg Briggs, for example, and others from other companies who provided their guidance over the course of what has been a fairly long program. So the two objectives of the project firstly started out with enhancing the health opportunities for our workers by reducing particulate emissions in particular, but making the systems that do that more robust. There are measures in place, but what we can see from some of the other talks is that ensuring those measures are effective and not continually used is one of the main challenges, and therefore a robust tamper-free solution is the best way to do it, avoiding opportunities for non-compliance. And the second thing to look at was reducing the cost of that compliance. We are in a cost-sensitive market, we compete globally, and therefore doing that effectively and efficiently monetarily is also an interesting point. The program, as a snapshot, spanned 2016 through to 2019. The first part of that work was to prove the concept. Could we take some technology that was available on road in heavy-duty truck sectors and bring it into underground coal? Would that work, and what were the challenges? After we did that proof of concept, ACARP approved a second round of funding for addressing the validation and industrialising that. And that included looking at surface temperature and how to make it in a safe, robust way, looking at blocking up from soot, and looking at thermal runaway and other concerns both the regulators and operators may have. All in all, we've achieved a lot of validation through dyno work. Engine dyno work allowed us to do the testing and development away from a mine site, so reducing the risk of that development process. Over 650 hours on the C7 engine and over 150 hours on the more legacy 316 engine. We also did some site-based trials. Centennial was very instrumental in assisting us with doing some work at Newstand, and PPK, who supported the project in kind, allowed us to do some site testing at a surface trial and allowed us to get some of those validation experiences that we needed. The first question's an easy one. Does the technology reduce particulates? And as you can see, the blue lines there are the engine out emissions, and the red lines there are after the wall flow filter, and I'll explain what a wall flow filter is and how it works. And in comparison to MDG 43's 2020 limit, they are all below that level, by at least half in many cases. they are fairly significant reductions in terms of percentage reductions, and you can see there that it's over 95% reduction, not only on the regulatory cycles, the NRTC and the NRSC, but also in some cycles that we developed for this project which represent real world operation, and taking those into a dyno room to evaluate how that performance is happening, both steady state and transient. A wall flow filter looks a bit like this, and this is a unit that's fairly commonplace now on heavy duty on-road trucks, also in light duty passenger cars. The technology that we've chosen has two parts to it. The first part is an oxidation catalyst, similar to what many of you are already using on your mobile plant, mobile diesel equipment, to reduce pollutant levels for hydrocarbons, CO. We use that for another purpose, and that is to generate some feed gas emissions that feed into the diesel particulate filter, which is the second part of the system. Now, both use a ceramic substrate. It could be silicon carbide, it could be chloride. The difference between the first element and the second element, the first element flows through, so the gaseous emissions are catalysed on the way through, whereas the second element has alternate holes plugged, forcing the gaseous emissions and the particulate emissions to go through that porous wall. And that porous wall effectively acts as a sponge to trap those emissions. So you're forcing it through the wall, therefore wall flow. When you look at the chemistry that's going on, it's fairly important to understand what changes you may need to implement for an industry where the machines are working at very, very low duty cycles. And we're talking here perhaps 50 or more than 50% idle time. So there's not a lot of heat in the exhaust that's going into these catalytic devices. And without heat, the question might be, do they work? The first reaction is pure oxidation. You have carbon, the soot, and you're trying to find some oxygen around which to oxidise that. And that needs some fairly high temperatures. As that graph shows, the blue line, peak optimisation, the peak efficiency of that oxidation happens at 500-600 degrees Celsius. Typical diesel combustion temperatures don't get up there. So therefore you're not going to get a lot of efficiency if you're trying to rely purely on oxidation of that carbon with oxygen. If you look at the second line there, another combustion byproduct there, NO2, does have a lower temperature of activation, a lower temperature of combusting that carbon that comes out in the soot. And the mechanism there is you use the first catalytic component to oxidise NO into NO2, and you use that as the carrier for the oxygen to enforce an oxidation at a lower temperature. So that's through those 2 or 3 stages, you are getting enhanced oxidation at a lower temperature, and that suits the type of application we are working here. This schematic shows a typical current disposable filter system and how we would transform that to be a wall flow filter system. The conventional system has a scrubber, it may have a catalyst. It has a scrubber there to drop the temperature of the exhaust effluent, and then uses a filter, a paper element filter typically, to trap those particulate particles. And once trapped, you dispose of that filter. The technology change essentially keeps many of those elements the same. So in terms of risk management, it is not completely revolutionising the approach. It still has a water scrubber to ensure tailpipe temperatures are maintained. And in between the engine turbo and that water scrubber is where the diesel oxidation catalyst and the diesel particulate filter are encased in an enclosure. We put the two together so they can communicate in terms of the gas exchange, and we encase those in order to limit surface temperature. And we've taken a novel approach of not just simply water cooling the whole assembly, but thermally managing that through a combination of insulation, which allows us to achieve the benefit of keeping those precious temperatures in the gas flow up high so that the catalytic process can continue, and also not waste energy into the radiator systems of the vehicle. If you can use it, we should use it. Joints and other things do have to be water cooled. It's very hard to insulate those effectively, and so joints are a water cooled feature. Some results here very briefly about the thermal management, the surface temperature management. You can see that where insulation is quite thick and accommodating, temperatures are quite cool, relatively cool, you can put your hand on it. In other areas where insulation is minimal, you can have to think very carefully about how you control the temperatures around that area. And water cooling of the joint is the main mechanism for extracting heat out of surfaces where insulation cannot be effective, and those of course end up being at the operating temperature of the coolant system of the machine. If we didn't have an insulated system, you'd have the performance of indicated in the blue line. So what this graph shows is the percentage of time that you have temperatures above a certain point. And in the design of the system, what we're aiming for is to have 40% of the time with temperatures over 240 degrees Celsius. And what that allows us to do is ensure the chemistry is favourable. And the blue line showing, yep, we do have a significant amount of time where we are able to reach that. It's just shy of that 40%. And that's because we have a very significant idle time. So when you idle an engine, it is not hot exhaust, and therefore even if you try and retain that heat, you're not getting up to the 200 plus degrees that you need. However, by insulating the assembly, you do retain all the heat that's available, and you can extend it to be over that bogey number of 40%. And when you look at the data compared to what you need for the chemistry, it kind of balances out. The majority of your time is in that sweet spot above 40 degrees Celsius, the 240 degrees Celsius. And if you do have some idle time, there is still some effective oxidation. It's just not the optimal amount. In validating that, what we do is we run a number of sooting tests where we repeat an industry-developed cycle around an LHD, a load haul dump machine, where we run that cycle over and over and over and over for a period of 100 hours. And we've run that cycle for both the C7 engine, an electronic control engine, and also the 3126. So 2 OEM partners contributed in kind to support this project with the engine, so we didn't have to go out and fund those. That was PPK Group and Sandvik. What you can see here, the results for the 3126 engine at various hours through that 100-hour process, and what you can see is fairly stable pressure across that DPF. The pressure fluctuates maybe 1.5 kPa over that duration, meaning that the sooting element has been stored, but it's continually regenerating and maintaining a stable back pressure. It isn't building up pressure and building up pressure and you have to do something special. Just the design of managing your temperatures and managing the location of that system is able to ensure stability. If that test is not hard enough, what we've also looked at is an extended idle test. The extended idle test looks at a prolonged idle where perhaps a machine is not fully utilised that day, perhaps for the whole shift, and in this case 19 hours, the machine is left idle, and the question asked is, does the back pressure increase? You can see during the idle phase, the back pressure is minimally changed, and we do a test before and after it to check at peak exhaust flow. Does that pressure change? And the answer is no, it's stable under those conditions as well. This is a picture of the system at test at Centennial, the first time we did some initial trial work. It was all surface trials. At this stage, we were looking at, does the apparatus fit into the machine? What areas of improvement do we need to do on the design? Are there any operational issues that we need to reconsider? The second trial, we used some more elaborate onboard monitoring systems to try and gather a lot more data about what was happening inside the can. You can see that the system looks like a pressure vessel. It is designed to be rated for explosion protection. The instrumentation is built into that pressure vessel, and that's one of the ways that we're able to use electronics and still maintain explosion protection. In terms of the electronics monitoring we used an electronic controller to record the data. That communicated with simple sensors such as pre-sensors for measuring temperature, pre-sensors for measuring pressure, so the pressure before the DPF, and post-sensors for measuring temperature and pressure. And the key parameters there are exhaust temps in, exhaust temp out, and the pressure across that DPF. So we're looking for changes over nominal conditions. We also use the opportunity to have some more advanced sensing technology there, technology that is becoming more and more commonplace on road. And that includes NOx monitoring, so monitoring of noxious emissions, and particulate monitoring. And particulate monitoring can be used for a number of things. In this instance, we're purely looking for, is there any breakthrough of particulates? Has the DPF stopped doing the job that we've asked it to do? The final trial, which was only completed in May this year, was also undertaken as a surface trial. It wasn't possible to actually get the exemptions in place that we were hoping for to do some underground work. That potentially is the next step. And what the graphic here shows is not only the machine and the machine out and the type of incline that we were using, but a reference loop that is part of doing some random workings around this site. We also used a reference loop to check on a daily basis, or every second day if not daily, under known conditions what that machine was doing. So that ended up being our reference point. Some of the data that came out of that, firstly is the simple stuff like engine speed and engine load. So you can see that as the machine goes up the incline, the revs go up, the engine load goes up. As it comes back down, the engine load's down, the revs are down. It shows that we can analyse that data and all the data points that came with it, not only for the temperatures, the pressures, the NOx and the particulates, but also that these correlate with how we expected them to be from the work that we were doing in the lab. There's a lot of data gathered in a trial like this, over 2 million points. So if we sat there and looked at every snippet of data, you'd get a graph like this, which really doesn't tell you a lot. It shows you, yep, there's a lot of transient running, yep, the engine got to coolant temp, the exhaust temps were this, the pressures were that, but it doesn't actually distill a big picture about, is this okay? Is this technology doing well? So distilling that data, we looked at a couple summaries, and I'll only present 2 of them. The ACARP report has been published in June, so you can go on the ACARP website and get more graphs than you care to want to look at. The 2 graphs I'll look at, firstly is temperature in terms of exhaust feed gas feeding into the DPF module. And more importantly than temperature is that percentage of time that we were over that threshold magic number. And as you can see, different days the machine was doing different duty, but on average it did satisfy what we recorded to be an industry typical operational duty cycle, where over 40% of the time would be sufficient to keep this system clean. How do we know that the system was kept clean? By monitoring the pressure across this DPF module over time, we looked at the maximum value in each snippet of data that we had. So at maximum exhaust flow conditions, which are at maximum power and at maximum RPM, did that differential pressure stay the same over the duration of the trial? And if it was in the green band, as you can see, it stayed stable, just like it did when we were testing this on bench. One of the reasons to test at site, rather than test just on a dyno, is you can't shake it and bake a whole LHD. So on the dyno you can cook the DPF and you can understand how that works. You can induce some failures knowing techniques that you do in the industry, but you can't take that whole machine with its solid tyres and rigid mounted exhaust system and subject it to the bouncing around of a mine site. So the trial was undertaken at a site that PPK made available. It was shaked and baked fairly extensively, and in a way that the OEM would do it and Orbital wasn't actually participating or controlling how rigorous that testing was. So it was done to try and prove out whether this system had a flaw. The final inspection came from looking inside the rear of that ceramic and seeing if there were any cracks or any fatigue marks or any blow-through of particulates. The photos aren't as good as they look when you look at it on the video with your own eye, but what it shows is there was no substrate damage, there was no fractures there, there was no blow-through, so there weren't any hot spots where the ceramic had melted or some plugs had come out of its DPF substrate and you were getting black emission soot marks or even thermal damage marks. So we were fairly pleased with those results, and no doubt the OEMs also looked favourably upon these. I mentioned that we also included in the trial some advanced technologies, and these were all around monitoring. These may not be things the industry chooses to adopt initially, but they are opportunities for the future. Many industries adopt these in terms of looking ahead and complying, not just retrospectively and not just feed forward. So rather than testing today and hoping that it's okay until the next time you test that machine, these are ways of testing every day and knowing and catching the anomalies, and also actively reporting those back into your maintenance practices. The first bit of technology was sensing for NOx. This is fairly commonplace now in heavy duty machines on road. It's similar to an oxygen ratio sensor, but what it tests for is noxious emissions, and knowing a baseline, you can compare that to a future result and see if there's an issue. The second sensor we had was particulate sensing. And the type of technology there we used was a resistive element type. So very simple. If you think of a little circuit board, it detects the presence of carbon depositing on that circuit board as a change of resistance. So it's able to say, yep, carbon conducts. The more deposited on there, the more carbon is coming through, the more soot's coming through the engine. We're expecting that value not to change because we've got a DPF there that's catching it, and if what's caught, it's turning into CO2, not carbon. So we expect no change in those results. If you look at the data again, it's very confusing. They're just trace histories there of ppms or resistance values. Not very sensible from a data processing point of view. So we use a number of filters and algorithms behind that to turn that into a meaningful answer. And a meaningful engineering answer is, have I changed from baseline? For example, in your NOx, you're allowed a plus minus 15% change from your baseline number. If there is no change outside that limit, all is good. And has the DPF continued to perform? If it's not seeing carbon, the DPF is intact, there's no cracks in it. Just to take that one step further in terms of the level of correlation, this graph looks at all the data for one run. So this is about an hour's worth of running, and you can see a whole bunch of bubbles there, and each bubble represents the level of NOx produced at a particular point as a function of speed and engine load. Again, to make sense out of that data is not easy for the human mind, but once you apply some filtering algorithms and say, okay, am I at quasi-steady state? What conditions can I use to determine that? Filter out the data that's meaningful. You can then compare it to some of the engine test dyno data we had, which is the red plots, and say, look, there's great correlation there. So just like doing a static test, you can do the real-time dynamic test and prove out the correlation. Similarly for the particulates, the runtime trace of resistance is not very meaningful, but you can then plot that resistance and its ability to regenerate that signal against a graph that looks at milligrams of particulates per cubic metre, and you can make a decision as to whether you're compliant or non-compliant. The ACARP project in its final year also undertook some investigations into the more in-depth aspects of the technology. Some of these questions were raised back in 2017 when I spoke here. Questions around particle size, what's the effectiveness on elemental carbons, does the system work with Aramanga UMF? All those technical studies have been done. I can talk briefly about them in question time, or you can catch me today or tomorrow and we can discuss those, but it's documented in the report. The additional work also did include not just testing the original program engine, the C7, but also looking at the 3126, because many operators still use that machine, and similar machines of that vintage. So we wanted to make sure that the investment that ACARP had put into this program was universally applicable, not just to one product or one OEM, but to the industry in a broader context. So just to summarise, I believe the program successfully completed and demonstrated that the proof of concept for a wall flow DPF could be applied to underground coal mining. The challenges took us probably 12 months longer than we expected to resolve, but there are solutions there, solutions which are generic and agnostic to what engine the system is applied to. The follow-on work did look at doing the industrialisation, so this technology isn't a lab project anymore. It is brought closer and closer to the commercial reality and application to machines that you use today. There were a number of additional technical investigations, and these technical investigations add to the knowledge base of the industry. So not just for these products, but also diesel emissions and the health of operators. And the validation work did indicate that the technology is applicable and mature. I do thank you for your attention. Happy to take questions or comments today or tomorrow.